today I want to focus not on everything that I am doing, but the part that I believe is like the most interesting to the general audience that we have here. But before, a little bit background about me. So I'm mostly interested in robotics, like perception, and specifically localization of the robots. So in 2018, I finished my PhD. It was about classical methods, optimization-based methods, how to fuse different sources of information together. And after that, I was doing everything. So I was doing like flying robots, I was doing legged robots. Right now, I am doing a little bit of underwater robotics. But the common thing is that I am doing it like from the localization, perception, and sometimes autonomy part that is the most interesting to me. So today's talk is a little bit about, can you really use all of the information from those robots? So the general idea is that in robotics, you take the camera, you take 3D LiDAR, you have abundance of data, and you try to do something clever with it, and you reject all of it, like most of it really, because you want to extract the information that is like the most accurate. But in reality is that if you wake up sometimes, you don't want to turn on the light, you don't want to use all of those sophisticated sensing modalities, you just want to complete the task. And this is like very similar to what we have like at night. You want to go to the kitchen, you want to drink water, you don't want to open your eyes, you don't want to turn on the light, and you just use this sparse kind of the information to be able to tell where are you. And this really stems from the fact that if you try to apply robots in some practical domain, sometimes you have to take into account that not everything works as expected. So it's like, in general case, you can do something with the camera, but if you go to the industry, if you go to the coal mine, for example, the conditions are not perfect for robots. They are like, it can be dusty, it can be humid, the temperature might not be right. And the question is that what kind of the other sensing modalities you can use to really tell where you are. Well, let's see if it works. Thanks. We can turn off the sound. Yeah, so this is like the walking platform that we had in our European project with ETH, Oxford, Edinburgh. And we were like focusing on the legged robots. The legged robots have this advantage that they can overcome harsh terrain. And we were like doing tests in coal mine. We were doing like underground and building them up, testing how it works out. But after those tests, we came with a really, let's say, nice idea, or a question maybe, research question, is that can you localize the robot just knowing where it put its feet? So you have just like the response of the terrain, force torque sensors, information, and you want to localize the robot in this terrain. So there's like nothing else. There is like no camera, no LiDAR, no external sensing, just having this internal sensors and trying to localize. So for our test, we gathered the data set that we had like the accurate lab, like accurate map of everything. We were like walking on slopes on these different terrains. We were tracking the robot movement, we were tracking the feet, gathering the data, and then this fun part starts. It's like how you can really use this information and how far can you really go in case of this localization challenge. So we were not first to really like try to design a whole theory behind it. So in robotics, you usually use sequential Monte Carlo particle filter. So you just don't know where you are, you have a lot of samples, and once you gather more information, you kind of know better where you are. And at some point, you converge to some localization, or you can track some localization. And this was like the baseline of our approach. That was also based on one of the works of our colleagues from Oxford. So what they really did is that they used information about height of the terrain, try to localize the robot. So they're like, if the leg is a little bit higher, it means that probably we're entering the ramp. And we are entering the ramp, you have a little bit of information, and therefore you can localize. At our university, what we were doing is that we were like classifying the terrain. So we were like taking just like the force torque input, and then determining if this is sand, if this is pebbles, if this is grass, and trying to have this information and then use it for the localization. At the beginning, the networks were quite huge. So very typical approach to like what you have in basic science. So you kind of fight for like those 0.5% of some particular case that you have better than the others. But in reality, those kinds of networks that are complex, hard to train, are very hard to deploy on robots. It's like you either not have real time, or it's really hard to work in different scenarios and different cases. But nevertheless, what we notice is that if you cross a terrain, so if you cross from one type of the terrain to the other, the robot knew a little bit more about its localization. So it was able to correct its previous estimate and be closer to the truth. But we completely didn't get any benefit if you are on the same type of terrain, because we are still walking and the classification tells you it can even be worse if you make a mistake. But the truth was that it is complementary. So if you have this information about the height of the terrain that Oxford University was doing, and if you have information about tactile sensing, about type of the terrain, then if you combine those kind of sources together, you get a little bit more information and therefore better localize the robot in this environment. But in practice, it's not very practical. I mean, having exact 3D map of the terrain always, like in the coal mine, it's not doable. It will be very hard to maintain, and it will be very hard to use, store, and also the network is too small, is too slow. So all of those kind of pushed us to look further. The other approach was, how far can we really go with terrain classification? I mean, instead of having those huge networks, can you just take a transformer? Can you just make it smaller, more efficient, and just get similar results? Maybe not as great, but close to. But on the other hand, much more accurate, much faster results, and therefore being able to deploy it on the robot. And the answer is yes. You can look at this problem from like a more practical perspective, trying like to measure the efficiency of this network. But it is also not that great. So you get better results, but they are still constrained to the discrete set of classes that you defined prior. So if we take a look at the natural grass, and if you take a look at the artificial grass, for us, it might be the same, or it might not be the same. It might look alike, but the response from the fork torque sensors might be completely different. So the question was that, is it really that if we define those classes as we believe them, is this the best approach that we can really go and use it for the localization? So the next approach was just try to completely forget about having classes. Try to not classify those signals, but try to encode them. Try to somehow make a compressed information out of it, store it in a map, and use it for localization. The benefit is that you no longer have those really preset classes. You kind of just encode, embed, however you want to call it, this information about tactile input. And in this case, we completely disregarded having like a full map of the terrain. We only have like a sparse, I will go back. We have only like a sparse set of places where we previously gathered the information. So you only have like those green places where the information was gathered. You no longer have a complete dense map, but each of those places contain this embedding. In our case, it was just an autoencoder at first and different other ways, but we had no control regarding this compression. It is mostly like compressing the signal, not having any impact what is stored there and what can be done. In this case, once again, we are using the same data set. Each of those embeddings are like compared together. We have some distance between them, and we use the difference in those embeddings to really update our information about the localization in the environment. So going with that, it turned out that we noticed that the robot is able to also make progress or be close to reality when it comes to the localization estimate if it's like walking on the same terrain type. So because it's not uniform, even in this laboratory environment, if you just put a sand there, it's not going to be the same sand everywhere. There might be like a more dense or higher, like more sand there or something. So the response is different, and therefore it can be used to better localize. But if you gather them together, it turns out that it is a reality. So it's hard maybe to say this, for example, if you have also information about the height of the terrain. But if you completely ignore the height of the terrain, so this is the odometry, this is like the classification, and this is just the compression with unsupervised learning, you get better results. So we are losing less information because you are no longer classifying to some discrete number of classes. From practical point of view, those values are not great. I mean, imagine a robot that would try to like go back from following the same route, but the root mean square error or absolute post error would be like half a meter. It's not great, right? It's like, in reality, it's really far away from truth. So the question is it something that we can do better? And in this case, we wanted to somehow be able to train the representation, be able to control what robot is really learning, and therefore have more impact how it can localize. And in our case, we took the architecture that we knew that is efficient, and we wanted to train it. In our case, we followed a triplet loss, very, very, let's say, popular choice if you are going for like a place recognition. So you have some anchor, and you have a positive and negative sample, and you try to make sure that the positive samples are similar to each other, while the negative is far away. In our case, we just assumed like a circular distance around the step, that we say that this is a positive sample, everything else should be negative. Knowing about the limitations of this approach, we were just curious if it is going to make a difference, right? If it's going to really learn something better for like data storage or embedding that will help us with the localization. And the results that we got were like without height, completely forgetting about height, is that it's much more accurate. It's like we can have a smaller embedding, we can localize it better, and that's great. Also, if you include the height information, you also get like the better results. But what is really important, if you take a look at this, is that we kind of no longer need like the height information. If you no longer need the height information, and if you only need like a sparse set of steps to really localize, it's doable to just put the robot somewhere, and it should be able to go back following the same route. So from the practical point of view of robotics, these errors indicate that hopefully, because we never really got to really test it in practice, if the robot, like camera or LiDAR, fails going and doing some repeatable stuff, the robot might be able to follow its footsteps and, example, go to the base. And in such a scenario, like in a coal mine, if the conditions are not great, it would be perfect because it would allow a little bit of autonomy, maybe not perfect autonomy, but a little bit more robustness in reality. So the conclusions that we had was that it is possible. We are so much closer to practice because it can be used together to just localize. But there are, of course, more questions than the answers, as usually if you open such a chapter in science. I mean, everything was done in a very controlled environment. Everything was done when there was like a clear distinction between classes. So it's not perfect, but this is robotics, and then you try to go further. So before we move on, I wanted to say to like the whole team that was at our university, especially Krzysztof that organized the founding, and also our colleagues, because this was like the part of the Think project. But this is what is really happening. Can we play it? So the animal robot is quite expensive. And in a sense, it's expensive that after 2 or 3 years of usage, it's like worn out. And if you need to buy another one, it's like a huge cost. So we went like with a Chinese robot that right now is equipped similarly with force torque sensing, IMU sensing. It has differential GPS, and everything is on this platform. The idea is simple. It's time to go outdoors. It's time to see how this approach will deal with if there are no clear distinction between classes. So imagine like a pavement, grass, and a little bit of pavement with grass. Is this method going to work out? Is it going to scale? So I would say one chapter has ended, and the other is already like opening that we are going to pursue. And that's it from me. Thank you very much for listening.